Okay, so we are moving on to chapter 2. In chapter 2, we are looking at chemistry, some of the smallest building blocks of the human body. So the title of the chapter is Chemistry Comes Alive, and yeah, I guess to a certain extent you can talk about it like that. Do remember though that this level, things are non-living. They certainly make up what we call matter, but they are non-living. We only get to an actual state of organization of the body when we get to the cellular level, because remember, each individual cell is a living thing. So that's the smallest living unit when we talk about the cell. But this is chemistry. In order to understand how we build cells and how cells maintain themselves, etc., we have to understand some chemistry. Now, this isn't a chemistry course, but we have to have a basic understanding of chemistry itself. So we're going to do one chapter through chemistry. And I like to do, something funny at the beginning of lectures. Sometimes I'll put comics on my exams and things like that. And I usually tell chemistry jokes, but really there's just no reaction. Get it? No reaction. Anyway, moving forward past that though, chemistry itself is going to be broken down into two different types. So we have biochemistry and basic chemistry. But it's going to be really what is creating all of the different, what we would call reactions that make up physiology. So we talk about function in the body and how things are moving and reacting and things like that. And it all gets down to chemistry. And when we get to these different body systems, like digestive system and the nervous system and things like that, we start talking about ions moving and molecules binding and things like that, and we have to understand the chemistry behind it. Okay, so as I was mentioning, certainly chemistry matters. It makes up matter, right? Matter is anything that occupies space and has mass. And to a certain extent, it can be seen, smelled, or felt. Now, it depends on how much of that particular substance there is making up that matter as to whether it would awaken those senses of you. But it does take up space, like we said. And when we talk about the mass of it, that is similar to what people think of as weight, but really weight is when mass is being pulled on by gravity. And so since we live on a planet that has gravity, mass and weight are kind of the same. But mass is, in truth, what we're talking about in terms of the amount of that particular substance. All right, so when we talk about matter, there are three possible states of matter, which you may be familiar with, particularly if you're talking about water, right? So there is solid, liquid, and gas. And so generally the solid is going to have a definite shape and volume. Liquid is going to be moving, etc., but still a definite volume. And then gas is a changeable shape and volume. So we have a lot of space generally in a gas where these molecules are floating around somewhat free. Now, one of the other things that we talk about in terms of chemistry is energy. Now, we know that it's a requirement of living things. We have to have energy, and it's the capacity, by definition, to do work or put matter into motion. And so what we find is that there's actually different types of energy as well. When we look at it, the types of energy that we have.
Energy is the capacity to perform work. Potential energy is energy that is stored. Kinetic energy is the energy of motion. Energy is neither created nor destroyed, but converted from one form to another. This property is called the conservation of energy. The bow and arrow start out with low potential energy. As the archer's arm pulls back the string, kinetic energy from the arm's motion is converted to potential energy in the tense bowstring and arrow. When the bowstring is released, the stored potential energy is converted into the kinetic energy of the moving arrow. When the arrow hits the target, its motion ceases. If energy is neither created nor destroyed, where did the energy of the flying arrow go? Let's rewind and look at kinetic energy in more detail. When energy is converted from potential energy to kinetic energy, some of the energy can be used to do work, but some energy ends up as heat, a type of kinetic energy. Heat is the random motion of atoms and molecules. As the arrow flies through the air, heat is generated by friction between the arrow and air molecules. When the arrow strikes the target, all the energy becomes heat energy. The heat energy is rapidly transferred into the air and spreads out. Heat energy is a very disordered kind of energy. It has the highest amount of entropy, or disorder, of any kind of energy. Where do our muscles get energy to perform work, such as pulling back a bowstring? Our bodies use the chemical energy from food to perform work. Chemical energy is a form of potential energy. When your body breaks down food molecules, the stored potential energy from food can be converted to kinetic energy. The stored chemical energy in food is released in your muscle cells during the process of cellular respiration. Using oxygen, cellular respiration converts chemical energy from food to another form of chemical energy called ATP. Water, H2O, and carbon dioxide, CO2, are byproducts of cellular respiration. The potential energy of ATP can be converted to kinetic energy. Some of the kinetic energy is used to do useful work, such as pulling back a bowstring, but the heat energy that is generated cannot be used to do work.
So in a way, when we talk about energy, right, we're turning it into seeing in this video, we can see how it really has a direct application in terms of how the body functions. And as we are homeothermic organisms, when we talk about energy being lost as heat, it's not actually lost or wasted on us, it's used to maintain our internal temperature. So chemical energy, as you think about it, as you take in nutrients and things like that, that is going to be used for energy, other types of potential energy, and then kinetic energy, the energy of movement for moving muscles, but also moving the digestive tract and moving cilia, etc. All kinds of things that we find in our body, in our living cells. Okay, so like we said, different types of energy: chemical energy stored in the bonds of chemical substances, electrical energy. There's also mechanical energy, radiant or electromagnetic energy, like coming from the sun, for instance. All of those are different types of energy. And to a certain extent, we use these types of energy like we see here. We don't use a lot of radiant energy, but of course, in order to perceive light, we have photoreceptors that will utilize that radiant energy to tell us what's going on around us in that particular sensation. Now what we find is, like in the animation, energy can be converted between different forms, and even though there is some of that energy lost as heat, in truth, we use that energy in a variety of ways. Okay, so we'll talk also about energy when we start talking about chemical reactions and we talk about enzymes and things like that, but we had to define energy to begin with. So let's get back then to chemistry in terms of our building blocks, starting with atoms and elements. So all of our matter that we talked about that occupies space and has mass is composed of elements. And the elements are basically these, pun intended, these basic substances that can't be broken down any further. Because if you break an individual atom down, it loses its characteristics and it gets broken into subatomic particles, right? Things like electrons and neutrons, etc. And so, again, kind of these atoms are a bit like atoms, which are the individual units of elements, are a bit like Legos. And so if you were to take a hammer to a Lego, break it into pieces, it's no longer that individual like 6 little piece block, right, anymore. So now it's just little broken pieces and it can't do its job anymore and it's lost its characteristic. So when we look at elements that are important to the body, when we're looking at biochemistry, there's only 4 elements that make up 96% of the body: carbon, oxygen, hydrogen, and nitrogen. So when we look at those, right, you'll see there's the C and the O and the H and the N. So we'll talk about the different chemical symbols and things like that as well. So you'll see these come up again and again, right? Carbon dioxide, water, H2O, etc. And so when we look at those 4, they're making up most of the body. And you're like, there's only 4% of these other things. That must not be important. But those other elements are very critical, life-sustaining. 9 other elements that make up most of that 4%. and then 11 elements that make up less than 0.01%. Now, again, when you look at those percentages, you're like, well, we could do without those things. You can't. There are some critical substances in the body, like magnesium or iodine, where they're used in very, very small amounts, but they have a very critical function that we can't do without. Okay, so getting back to these elements though, a periodic table like you may have seen in the classroom or in the lab or in your chemistry class lists all the different known elements. And so when we're talking about those elements, like we said, the basic unit of an element is going to be an atom, a unique building block for those elements. And when we look at them, an individual atom, when we look at that element, it has its particular, like we said, physical and chemical properties. And if you go smaller than that or you break it up, then it's going to lose those unique characteristics. So when we look at an individual atom of an element, it's got a symbol, like we said, like carbon and oxygen and hydrogen and nitrogen, COHN, like we see there. Some of those are straightforward. Other ones, they're not quite so straightforward. Some of them come from Latin, where you see sodium, like we see here. Natrium comes from its Latin name. Kalium, K for potassium, because it's not P. So some of them aren't quite so obvious. Einsteinium, that one's pretty obvious, but again, they all have an atomic symbol to be able to identify them. Now we said that if you break these atoms apart, they break into their subatomic particles. So when we're looking at a particular atom of an element, it's going to have a specific number of these components, these subatomic particles. Those protons, which have a positive charge, right? So if you're pro for something, if you're for it, right, you have a positive feeling about it, you support it, right, you're pro. Protons carry a positive charge. They have a unit of basically one atomic mass unit, or MU. And then we have neutrons, which are neutral. They have no charge, right? If you're neutral, you don't go one way or the other, you're right in the center. And those also have a weight of about 1 MU, if you will. And then we have electrons. And electrons have a negative charge, but they have a very, very tiny mass. So they have virtually no weight. When we say 0 MU, if you will, that 0, if you were to carry it out in decimal places, you would get to a point when it would actually have units to it, but it's relatively small. So again, remember, even electrons themselves, subatomic particles, are going to have mass and take up space. But that mass is very, very small when you're calculating it in terms of contributing to the mass of an individual atom. Okay, so when we look at an atom, we have the number of positive protons, remember these are positive, plus, and the number of negative electrons. Those numbers are actually equal in a given atom, and so they're electrically neutral. And of course, any neutrons that it has, those also have no charge. So they're electrically neutral, and in terms of how chemists have diagrammed an individual atom, they're looking at the distribution of these different subatomic particles. And the protons and the neutrons are generally found in the center, in an area that's called the nucleus, much like a cell has a nucleus. And then the electrons, the negatively charged electrons, are going around in an orbit, much like you think about the moon going around the Earth or the Earth going around the sun. They have an orbit that they go around that nucleus. And they have a kind of a complex pattern, so once upon a time they kind of designated them like rings, again like the moon around the Earth, but now a lot of diagrams designate them more as a cloud of their patterns that are swirling around. So that's kind of the difference between what we call the planetary model and the orbital model, like you see here, designated for helium, He. So here we see 2 protons, 2 neutrons, and then 2 electrons, right? We always have the same number of electrons as our protons. And when we look at it, this is the planetary model, right? You see on one particular orbit or path, and this is more of the orbital model where we see them kind of traveling in many different orientations. Okay, other things that we see about these different atoms, if we look at particular elements, here we see hydrogen and helium, He, and lithium, Li. So when we look at the number of protons, neutrons, and electrons, they're different between them. So that's how we can determine the characteristics of these different elements, right? Hydrogen, 1 proton, 1 neutron. We said that those are all equal. Have no neutron though. When we look at helium, helium have 2 protons, 2 neutrons, and of course balanced out by 2 electrons. When we get to lithium, it has a higher mass still. Now we see 3 protons, 4 neutrons, and then 3 electrons to balance out those 3 protons. So you can see how their mass of these individual elements go up and up and up. And when you look at a periodic table, you can actually see the mass going up along with that atomic number and atomic mass. Okay, so we identify these elements according to atomic number. That has to do with the number of protons in the nucleus. And when we see the symbol like Na or C or something like that, it's going to be a subscript to the left of the symbol. So that, the atomic number equals the number of protons in the nucleus. So lithium was 3, hydrogen was 1, helium was 2, etc. in terms of the atomic number. The mass number is when we add up the protons and the neutrons in the nucleus. Now remember, each of those each proton and each neutron has a mass of 1 mu, and so we just add those up, and that's going to be the mass number. Now again, if you were really calculating it out, you would also add in the electrons, but those are like out at the 6th or 7th significant digit, right? And so you can kind of round that off. So gives us the total mass of the atom, and this is written as a superscript to the left of the symbol instead. So we can see how it's up above the atomic designator that we see there. Okay. Now you may also hear about what we call isotopes, and isotopes are different variations of the same element. So these are going to have the same number of protons, but they differ in the number of neutrons that they contain. So for the same individual atom, what we have is variations on that element. So we're going to have different number of neutrons inside of it. So atomic numbers then are going to be the same because the proton number is going to be the same. That's the same as the atomic number, but the mass numbers are going to be different. So we can talk about isotopes. So for instance, carbon-12 is the most common form of carbon that shows up. And so it has 12 neutrons inside of it. But you also have carbon-13, carbon-14, etc. And so those different types of isotopes, they have, again, different numbers of neutrons to them, so they have a different mass number accordingly. And those other isotopes generally are not very stable, so they tend to fall apart through time, and they give off energy, radioactive energy, so they call that radioactive decay. So you may hear about carbon dating and looking at the proportion of certain isotopes of carbon or other isotopes of other elements and how they are decaying through time and giving you a gauge on the approximate age of that particular substance. Anyway, all right, so we have isotopes, and then we have atomic weight, like we said. So the atomic weight overall is the average of the mass numbers of all the isotope forms of a particular atom. Like we were talking about, whether it was carbon, or in this case we have, for instance, hydrogen. So we have hydrogen, which has 1 proton and 1 neutron. That's the stable common form, but there's also deuterium, which, like we see here, has an additional neutron to it. Or tritium, which has 2 additional neutrons to it, and obviously that's going to significantly affect the mass. Now again, this is their most stable form, but if we're looking at the mass itself, we look at, for the weight, we look at the average of all those different mass numbers. But in general, because those different subatomic particles have different masses like we see, and the electrons almost negligible, we just basically add up those protons and the neutrons to get that atomic mass or atomic weight. Again, when we get into the isotopes and things like that, that's a little bit further than we'll need to know for our biochemistry, for anatomy and physiology, but we mention it because you do hear about it as well. So, like we said, like in terms of radioisotopes as well. Isotopes that decompose to get back to that stable form, get rid of those extra neutrons. So radioisotopes can be used for labeling as well. So you sometimes hear about that. They'll have some radioactive iodine if they want to see what's going on with, there's a gland right here. Everybody know what the gland is? It's right here. The thyroid gland. So the thyroid gland uses iodine from your diet, and so if you label that iodine, you can see and image that thyroid gland a bit better. In any case, that radioactivity, that energy that they give off, it damages tissue, but to a certain extent, you can be very careful with it, very low levels of it. But you also hear about radioactivity being used in terms of you can get cancer from it, but you also hear about radioactivity being used to destroy cells intentionally as well. Okay, so started with the building blocks. Those are atoms, right? Atoms of individual elements. So those are the individual building blocks like the individual Legos. But the next step in our sequence of complexity of the body, we go from the atomic level to the molecular level. Still chemistry, but we are moving up to when we have these individual Legos and we put them together, and now we're forming something more complex. So we'll see that in the next step.